February 2025, a researcher at MIT watches data stream onto his screen. 12 hours of observation with the most powerful telescope ever built. And he writes a sentence in Nature that no astronomer had ever been able to write before. What he found challenges everything we thought we knew about the death of galaxies. But before I tell you what it is, we need to talk about a problem that physics says cannot be solved. Because the object at the heart of this discovery should not exist, according to every equation, according to every model, according to the mathematical limits of the universe itself. And yet, it's there, 5.8 billion light years from Earth, 100 billion times the mass of our Sun. It's called Phoenix, a star. Here's something that's rarely explained properly about black holes. A black hole doesn't grow freely. It chokes itself. As it pulls in gas, that gas forms a swirling disk heated to millions of degrees. That disk radiates energy, and that radiation pushes surrounding gas away before it can fall in. This limit is called the Eddington limit. It's as real as the speed of light. And it says this: the most voracious possible black hole doubles its mass every 100 million years. To reach 100 billion solar masses from zero, it would take about 40 consecutive doublings without interruption, starting from the earliest fractions of a second after the universe began. The universe is only 13.8 billion years old. And Phoenix A star formed between 10 and 100 million years after the Big Bang. It had less time than the theoretical minimum required. So now, here's the real question. How did a physically impossible object become the most massive in the observable universe? Astrophysicists have three answers. None are simple, and all three may be true at the same time. Concretely, what are we talking about? If you fuse together all the stars in the Milky Way, the 200 to 400 billion stars in our galaxy, you'd get something on the same order of magnitude as Phoenix A star. In a single point, its event horizon, the boundary beyond which even light cannot return, spans 590 billion kilometers in diameter. The distance from Earth to Pluto is 6 billion kilometers. Phoenix, a star's event horizon, is 100 times larger. Traveling its circumference at the speed of light would take 71 days and 14 hours. In 2024, a team from Yale University published something astonishing. After modeling the physical limits of black hole growth, they concluded that the theoretical upper limit sits at around 100 billion solar masses. If their calculation is correct, Phoenix A star is not just the most massive ever detected. It is the most massive we will ever detect. The universe produced an object sitting exactly at its own physical ceiling. But then, how is it there? Here are the three scenarios. First scenario: Galactic Cannibalism. The Phoenix cluster is one of the densest environments in the observable universe. Hundreds of galaxies collide there. Their central black holes merge with them. Simulations published in the astrophysical journal Letters show that triple mergers, 3 supermassive black holes merging simultaneously, can produce black holes exceeding 50 billion solar masses. 2 such cascading events could theoretically be enough. Second scenario: Super-Eddington accretion. In November 2024, the James Webb Space Telescope observed a black hole consuming matter at 4,000% above the Eddington limit. Not for a fraction of a second. Sustained, measurable, published in Nature Astronomy. The Eddington limit is not an unbreakable wall. Under certain conditions, a black hole can grow much faster than classical models predict. Third scenario, a primordial origin. In the earliest fractions of a second after the Big Bang, quantum density fluctuations may have triggered direct gravitational collapses. No star, no supernova. Primordial matter collapsing into a black hole before the first star in the universe even ignited. A primordial black hole of 10 billion solar masses formed in those first moments would then have had 13.8 billion years to grow, without violating any rules. Remember the MIT team from the beginning? The 300,000 Kelvin gas they were looking for? Here's what they found. And this is where everything changes. A black hole as active as Phoenix A star should be a galaxy killer. Its relativistic plasma jets, beams of energy launched at fractions of the speed of light, should blow away interstellar gas, shutting down all star formation. That's what every other active supermassive black hole we know does. Phoenix A star does the exact opposite. Its jets carve cavities into the hot gas of the cluster. Along the edges of those cavities, the gas cools from 10 million degrees down to 10,000 degrees. Passing through that intermediate 300,000 Kelvin gas, that warm gas keeps cooling. It forms cold filaments. Those filaments collapse into stars. 740 new stars are born every year in Phoenix A star's host galaxy. The Milky Way produces one or two. The most massive black hole in the observable universe uses its own destructive jets to trigger a storm of star formation. This is not a cosmic graveyard. It's an engine. This is what the MIT discovery really proves. Phoenix A star is not a passive anomaly. It actively orchestrates its own galaxy. Its jets, once thought to be destructive, are actually the mechanism generating those 740 stars per year. And that changes something fundamental in our understanding of the universe. The Eddington limit is real. The universe's time constraint is real. And yet, this object exists, sitting exactly at the theoretical upper limit of what can exist. This is not a coincidence. It's a symptom. The universe has growth pathways we do not yet know how to model. Every new observation will tighten the constraints. The Next Generation Event Horizon Telescope, Future Gravitational Wave Detections by LISA. And maybe, one day, a definitive answer to how this 100 billion solar mass monster could have formed within the time allowed by our universe. But there's another question this discovery leaves open. And it concerns what happens when a black hole of this size starts to die. We'll discuss that in an upcoming video. Thanks for watching. I hope you enjoyed the video. If you'd like to support the channel, please subscribe. It's free. See you soon for another unforgettable and exceptional journey into the heart of the wonders of space.